Acid-base titration, example 5. For part A, calculate the volume of base needed to reach the equivalent point. So what do I know here? I've been given the concentration of a weak acid and the volume of solution. So to calculate the number of moles of acid present, we just use the formula. Moles could be found as concentration times volume. How many moles of base? Each acid molecule donates one hydrogen ion. It is a monoproctic acid. So what does that mean for the titration? It means that 1 mole of strong base is needed to neutralize 1 mole of the acid. So the number of moles of base needed to reach the equivalence point here is equal to the number of moles of acid. Now, using the concentration of the base, I can solve for the volume of base needed, as volume equals moles divided by concentration in molarity. And that wraps up part A. Part B asks you to calculate the pKa for the weak acid. To find the pKa, I just need the Ka, the acid dissociation constant. It's either given or calculated earlier. Once I have that, I simply take the negative log of Ka, acid dissociation constant. So it's quick and simple. Now just ask yourself, does the pKa make sense for a weak acid? It should fall somewhere between 3 and 7. Part C, determine the pH of the original acid. Okay, so we're going on here to think about when the titration starts. The weak acid partially disassociates when it is added to water initially or inaugurally. This creates an equilibrium between the undissociated acid, its conjugate base, and hydrogen ions. So using the Rice table, we have the initial concentration of the weak acid. We have no hydroniums and no or zero conjugate base. As the reaction progresses, the concentration of the acid decreases by the amount X, while the concentrations of the conjugate base and hydroniums each increase by that amount of X. After the shifting has occurred, X will be equal to the hydronium concentrations. Substituting terms of X, since X is small compared to the initial acid concentration, we can simplify the expression, and this avoids the use of the quadratic formula. Solving for X using the case of A value tells us the concentration of hydronium ions after that inaugural shifting occurs. So what does that mean? It means pH is simply the negative log of that X value, which is now the value of H3O+. This also gives us our initial point on the titration curve, the pH before any base is added. Guess what? Shortcut. Remember, your pH equals 1/2 the pKa minus the log of the concentration of the acid. It's nice to verify that the two methods give similar results. Memorize your shortcut, folks. It could be very useful. Part D, sketch the titration curve. It starts with the pH that we just calculated, the weak acid's initial pH before any base is added. As base is added, the pH rises gradually, especially during the buffering region. At the half equivalence point, the acid has been neutralized. Half of it has been neutralized. And at this exact volume, the concentration of acid equals the concentration of conjugate base. So pH equals pKa. Earlier we found the concentration at full equivalence to be 47.1 milliliters in this example. So half equivalence occurs at 23.6 milliliters. Also, we found the pH at half equivalence to be the same as the pKa value. At the equivalence point, all the acid has been neutralized because we're titrating a weak acid with a strong base. The solution now contains only the conjugate base. So its pH is above 7, somewhere in the basic range. After the equivalence point, excess strong base will dominate, and the pH quickly climbs before leveling off near the top of the curve. It is not a straight line. There's a shallow rise at the beginning, a buffering plateau, a steep vertical jump at the equivalence point, and then a leveling off as more base is added. And that's it, a full titration curve from start to finish.